Now, I forgot to mention one aspect of drawing Lewis structures. When you get an equivalent structure like these two, the only difference is there's a you know, a 180-degree rotation here. The molecule likes that from a stability standpoint because it spreads out. Remember, there are 4 electrons here, 2 pairs. Now, the 2 pairs are not equivalent. One is called a sigma pair, and the other is called a pi pair. The pi pair is more unstable than the sigma. So just looking at this one here, we've got a sigma bond, and a pi bond. By sharing that unstable pi bond in 2 different places, it achieves a more stable version. So what it does is it goes back and forth, back and forth. So the way they represent that, it's called resonance, like resonating in terms of an audio wave. They represented it with dotted lines here. And the dotted lines represent the pi bond. That's pi, just like the numerical constant pi. Okay, so whenever you can draw equivalent structures, think resonance. And there's a fair amount of these examples. This happens to be ozone, but there are many, many other examples as well. Okay, let's now zoom over to the next chapter. I'm really glad this book brings in biochemistry and physiology. It's kind of interesting. One of my specialties is carbohydrate chemistry. And it's very interesting why some carbohydrates are much sweeter than other ones. And it has to do with this right here. Now think enzymes. All enzymes have active sites by definition. The active site is a 3-dimensional kind of cave within the enzyme molecule. The substrate reacts inside that molecular cave. In the case of tasting, these are then aligned with some areas of your taste buds. The interesting thing is, for you to taste something sweet, it's got to fit in there. If it doesn't fit in there, it's not sweet. Okay, so the common sweeteners are sucrose, glucose. Everyone knows about fructose, but there are others as well. There's even scales, and sucrose is the relative. Everything compares to sucrose, which is your common table sugar. Fructose is much more sweet than sucrose. Fructose by itself. Glucose is not particularly all that sweet. It's an important molecule physiologically, but it's not all that sweet. It's sweet, but nothing compared to fructose. And when you combine the fructose and the glucose together, you get something kind of in between. Interestingly, you have an enzyme in your mouth called amylase, which takes any carbohydrate and cleaves it from a polysaccharide down to a monosaccharide. And these are big sugar units that come off that big sugar molecule. So when you take sucrose into your mouth, within seconds, you create glucose and fructose, because sucrose is a disaccharide made up of those two with some special binding between those called glycosylic linkage. Okay, so you're basically eating fructose and all the ramifications of overload of fructose in your body. Things like what happens in your liver, what happens if you have cancer in your body, a whole bunch of stuff. So basically, it's got to fit into this active site. And if the active site changes through manipulation of pH, through heat, number of things, then that active site isn't as available anymore, where that substrate, sugar in this case, will fit in there. But other things can fit in there as well. If something else will fit in there, you taste sweetness. For example, sucralose. Sucralose is a modified sucrose, and the OH groups on the sucrose are substituted with chlorine. So what happens is the sucralose fits right into that active site because it's exactly like sucrose, only no hydroxide, it's chlorine instead. So your mouth goes, ah, sweet. But when your body amylose tries to take it apart, it can't because the chlorine is not a hydroxide group. So all these little things in terms of three-dimensional shape really make a big difference in terms of how your body reacts. Your body really sensitive to this. Monosodium glutamate, MSG. Your body makes glutamic acid, which is an amino acid, every microsecond of the day. Make it all the time, okay? If you take that glutamic acid and take off the H group, like with a base, you end up with glutamate. So then why is monosodium glutamate so bad for you? It's because amino acids and carbohydrates both are in two different optical forms or three-dimensional shapes, D and L. Your carbohydrates, the natural ones are D. For amino acids, they're L. When you buy MSG at the store, guess what? You don't get L, you get a combo of D and L. So the question is, what does the D MSG do to your body? And that's what some people are allergic to. But again, it's just a three-dimensional shape. Another example is, who's heard of thalidomide? Anyone? Thalidomide was a disaster in the 60s. It was given as an anti-nausea drug to pregnant women in the first trimester. And it also exists as DNL. But at the time, they didn't separate the two. They just said, here you go. And what happens is it causes massive birth defects. And the birth defects didn't kill the fetus. What happens is they had no arms or legs. Yeah, I mean, it was particularly in Germany, it was really bad. And the difference between the two, one was a nausea drug, the other was a teratogen, was D and L, three-dimensional shape. So it's a big deal in our bodies, a big deal. When you get into carbohydrate and amino acid research, that comes up all the time. And they're called enantiomers of one another. In fact, one of the drugs I'm taking for my cough is an enantiomer. And they were very specific about making sure I got the right one. So, and it costs a lot more to make because you have to purify the D from the L. Chemically, same formula, same shape, except for one big difference is they're a mirror image of one another. Just like our hand. One palm, 5 fingers. One palm, 5 fingers. Are they the same? They're not. They're a mirror image of one another. One will fit in certain places, one will not. Yeah.
It's like virality.
It's like what?
Virality. Like shape it.
Yes. Yes, and it's something that's chiral. Usually there's a D and L form. Not all the time. It depends. Chiral, remember, to be chiral, you have to have independent groups as opposed to like if two high, and you have to have 4 also. So they're just 3, or if you have chiral is the basis of this D and L, everyone. Never heard of this before. She's had a bunch of biochemistry, that's why she keeps asking this question. But yeah, it's chirality, I don't know how the word, the concept of being chiral, yeah, ends up producing these D and L forms. which is an MCAT question usually too, by the way. They ask you to identify how many chiral carbons are on various carbohydrates. No. Probably on a vet test too. All right. Okay. And of course, that's where the artificial sweeteners come in because they also fit the active site. Probably the artificial sweetener frequently does other bad things. Okay, so what we're going to get into today in the dry lab is going to be something called valence shell electron pair repulsion. And no one wants to blurt that out. They usually say VESPR. So that's what your worksheet today is titled. Okay, the idea here is electron groups repel one another to be more stable. So basically, the way I do this is I use metaphors with this all the time. If you had your parent and you've got two bratty kids that are just always fighting and stuff, two kids, and you just had your day, you're done with it, what do you normally do?
On the TV.
You threaten them, huh? What?
On the TV.
One way is to separate them, right? What would be the best way to separate those two bratty kids?
Trebuchet.
Obviously, you're not a parent. What do you think the best way to separate those kids would be? Keep them in the same room? Yeah. Separate rooms. You want to separate them. And you want to maximize the distance. Two bratty kids. Maximize the distance. Okay. Or two electrically charged electrons. The most stable configuration for that would be to have them as far apart as possible. What if you had three bratty kids? Same concept, only you have three now. Oh, let's see here. If you had four, now, interestingly, two dimensions. What if you had four? Same concept, right? But would it be 2-dimension? Or would it be 3-dimension? So there's two versions of 4. Okay, but with 4 electrons, by going into the 3rd dimension, you can increase the separation. Again, increase the stability. Okay, so this nucleus would be in the middle of this pyramid, 4-sided pyramid. This would be a quadrahedral. And if we had 5 electrons, 6 electrons, same idea. From 4 on, it's all three-dimensional. Maximize separation, maximize the stability. That's the name of the game. because electrons repulse, which is unstable, you want to minimize the repulsion by keeping them as far apart as possible. That's the basis of this whole thing. Because with Lewis had a problem with this. Lewis that's what Lewis projected for water. Linear. Water is not linear. Water looks like this. If you include the non-bonding pairs, see, that's the trick. You include the non-bonding pairs like you would an atom. So there are 1, 2, 3, 4 separation phenomenon going on here. Hence it's a tetrahedral. But you can't see those 2 pairs. So it looks like it's bent. And that's consistent with the polarity of water. Water is very polar. In this situation, we'd have water being non-polar because we have 2 vectors here and they are directly opposed. And because it's an OH and an OH, the quantity would be the same. And those would cancel. Hence, you wouldn't have any polarity if it was a linear molecule. Now, if you look at this, this is lopsided. Now, when you're trying to figure out whether a molecule is polar or not, I want you to look at if oxygen is present. Single bonded oxygen. If it is, it's always angular like this, not symmetrical. Nature likes symmetry. Something's unsymmetrical, it's not as stable. Okay, so in this situation, whenever you have an oxygen, single bonded oxygen like this, doesn't matter what's over here, it's going to be a polar molecule because it's unsymmetrical. And there's all those little cutesy calculations you can do and you end up in the same place. Look at it. Is this a symmetrical molecule? Yes or no? And if it's got oxygen there, single bonded oxygens, usually it's polar. Like an alcohol like ethanol, drinking alcohol, 2 carbons and an OH group. OH group. OH groups have 2 single. That means alcohol is polar. What's vodka? Ethanol, pure ethanol. That's called Everclear. And what is it, the alcohol mixed with? Water. Always vodka with water, okay? And notice when you look at a bottle of vodka, does it look like there's an ethanol layer and a water layer? Or does it look like plain water, one layer? One layer, because ethanol is very polar and water is polar. Remember, like dissolves like. And the reason why ethanol is so polar is because of the single bonded oxygen in there. Isopropyl alcohol. Isopropyl alcohol is a 3-carbon alcohol with the OH group in the middle. So do you think when you buy rubbing alcohol, it's pure rubbing alcohol? There's like 50%, 70%, and 95%. All those are mixed with water. When you buy vinegar at the store, it's not pure acetic acid. It's not glacial acetic acid. It's 5% vinegar, 95% water. They mix really well because vinegar hasn't not only an OH group, it's got a C double bonded O in it as well. So acetic acids are very, very polar. Mixed with polar water, they mix really well together. So it's important, particularly if you go on in chemistry, from a molecular biology or a biochemistry perspective. Did you talk about polarity a lot in biochem? A lot, yeah. Yeah. And when you get into physiology, particularly cell physiology, you talk a lot about membranes. And our body is a big sack of water. And that's a problem because we have to do different things in different parts of our body. So how does our body separate one water reaction from another water reaction? Membranes. Membranes are non-polar. They're made up of phospholipids. Okay, so your body then creates these non-polar enclosures, basically. So the polar water reactions are separated from the other polar reactions. And that's how your body gets away with this problem of all these water reactions all mixing together. Keeps them all separate with membranes. And there's nuclear membranes, cellular membranes, a whole bunch of different kinds. And they're basically built up with non-polar fat. They're called triglycerides. And you put on one of the triglyceride parts, you put a phospholipid there instead. But they basically look the same. Okay, so polarity is really a big deal. Okay. All right. Much of the VSEPR analysis is done on a central atom. Okay. A central atom is where all the analysis is done. So question is what's a central atom? Okay. All right, everything talks about central atom this, central atom that. So you need to be able to look at a molecule. And first thing is determine how many central atoms are in that molecule, because that's where you do the analysis. Just because this molecule has 3 atoms, it only has 1 central atom. Central atom is defined as an atom with 2 or more atoms bonded to it. Okay, the oxygen has 1, the other oxygen has 1, but the nitrogen has 2. So this has 1 central atom. Okay, we're going to look at this amino acid, actually. This is called glycine. Okay, so how many central atoms are there? Well, the hydrogens never are central atoms because they can only have 1 bond. Halogens can only have 1 bond, so they're never central atoms. Everything else can bond twice. Okay. Carbon here. How many bonds are attached to it? 3. So bam, central atom. Oxygen, 2, central atom. Carbon, 4, so central atom. Nitrogen is 3, central atom. None of the hydrogens. Oxygen up here, central atom. Only 1 bond, so it's not a central atom. So when we do a VSEPR analysis of glycine, we will have to do 4 analyses, 1 per central atom. And depending on how many bonds we have to the central atom, it'll come up with 5 different configurations. Could be linear, could be trigonal planar, could be tetrahedral, it could be bipyramidal, Now, a whole bunch of different combinations, but there are 5. Okay, if there are 2, so central atom, if there are 2 groups, it's called linear. Now, an electron group, what constitutes an electron group? Think of electron group as a group of electrons. Let's look at this carbon here. Group of electrons, that could be 2, 4, or 6 electrons. In other words, single, double, triple bonds. So carbon here has 2 groups, hence it's linear. Beryllium, 1 group, 1 group. It's 2 groups total, hence it's linear. Now I want to specify it isn't just a linear geometry. Okay, we're going to have the electronic geometry is the geometry of how the electron groups. Here, let's are arranged. Has nothing to do with what's attached to those groups. Okay. We have molecular geometry. Molecular geometry is looking at okay, with molecular geometry, we're differentiating between bonding and non-bonding electron groups. Electronic geometry doesn't care. Molecular geometry does. The molecular geometry is how it looks. For example, water. Water has four electron groups, and it has two bonding. That's the OH, and two non-bonding. So the electronic geometry for water is tetrahedral. It doesn't care what's bonding or not. The molecular geometry for water is bent because the non-bonding don't count. So you have to look at both of those. The first thing you do is an analysis of the electron groups. So in this case, these are linear, and to be linear, the group geometry and the molecular geometry are the same. So linear is the most simple. Okay. So if you have two electron groups, bam, linear. Next question is, how many bonding groups do you have? 2. How many non-bonding groups? 0. That means the molecular geometry is linear also. Okay, so what we're going to do now is just start adding electron groups. Oh, and then the angle is 180. You also need to know that. Okay, we have 3 electron groups. We end up with something called trigonal planar for electron geometry. And depending on whether we have atoms bonded to those electronic groups, we're going to have either bent molecular or trigonal planar. So you end up with 2 versions. And the bond angle is 120. Okay, so 2 versions. Okay, we have 3 electron groups. So the electronic geometry is trigonal planar. How many bonding groups do we have here? 3. How many non-bonding? 3. Look at this. How many electron groups do we have? 3. So the electronic geometry is again trigonal planar. Okay, and how many bonding do we have here? 2. How many non-bonding? 1. So when we have a situation, we have 1 non-bonding, 2 bonding, that's called bent, similar to water. Okay, so electronic geometry for both of those molecules is trigonal planar. The molecular geometry is not. That's going to be trigonal planar. And this is going to be bent. There's some more examples of these as I go along. Okay. So remember, for geometries, you always have 2. No exceptions. You always have 2. Electronic geometries is a geometry of the electron groups. It has nothing to do with what's attached to them. When you get into molecular geometry, it depends whether the groups are attached to something or not. Then that determines a shape. Sometimes it's the same as the electronic one. Sometimes it's not. Frequently, it's not. Four groups. Tetrahedral is the main electronic geometry. Doesn't matter if this is 2 H's and a chlorine and a fluoride, got 4 electronic groups, regardless of the atoms attached. Okay, so whenever you do the analysis, you take the central atom and you cover with your fingers the atoms attached because they mean nothing in the analysis. It's only the electron groups, the bonds themselves, the bonding valence electrons. And because they're 3-dimensional now, instead of 2-dimensional, the angle is 109.5. Now 109.5 assumes that all 4 of these are the same. We throw a chlorine up here, it's not going to be 109.5. Be something else. The electronegativity is different. The bond length is going to be different. A number of different things are going on. Okay. When you have 5, that's when you have 2 trigonal pyramids stuck together are trigonal bipyramidal. Okay. Electronic geometry. Now there's a whole bunch of options when we start getting into 4, 5, and 6 versions of this for the molecular geometry. So the simplest geometry is always electronic geometry. Now the thing about 5 and 6 position molecules is you have polar atoms and equatorial atoms. Now, the relationship between the equatorial atoms is 120 degrees. The relationship of the polar atoms is 90 degrees. So just think of the Earth. You have the core of the Earth, then you've got stuff going around the equator, and those are equally distributed. Then you have the 2 poles, opposite one another, except on our Earth, things are different. Okay, and then when we talk about 6, and we end up with an octahedral. And again, we have polar regions and equatorial regions. Now, this is a very common setup when you get into periods 4 through 7. Very common. This is used to explain metallic chemistry. Yeah, things like chelates and all kinds of interesting things. So octahedral, and the problem with octahedral is there's a whole bunch of versions of molecular, depending on what the setup is. For example, say you had electron pairs here, as opposed to electron pairs in the middle. It varies a lot. Now, a lone pair is an electron group. A bond is an electron group. They both have 2 electrons, but they're not equal. They're not equal at all. Electron pair electrons tend to be closer to the central atom. They tend to be closer to the central atom. A single electron pair is the furthest from the central atom. A double bond is closer, triple bond is closer, and the closest is a lone pair, a non-bonding lone pair. And that's going to affect the angles. Because if you're closer to the central atom, for example, with a non-bonding electron pair, the effect of the repulsion is going to be greater than if you're further away. That's why water is 104 degrees and not 109. Okay. I'm going to take the, the basic tetrahedral model here and show you all the versions of the molecular geometry. So let's take let's see. Okay, so let's look at take that suspected spam. Okay, okay. So let's take chlorofluoromethylene. Okay. All right, let's analyze this now. First of all, how many groups, electron groups are there? First of all, carbon's the only central atom here. So we're doing the analysis on the per central atom. So the central atom is carbon. So for the central atom carbon, how many groups are there? Electronic groups. 4. That automatically makes it a tetrahedral geometry. Okay. How many lone pairs are there? Non-bonding lone pairs. We're only doing central atom, carbon. 0. How many bonding? Okay, that means the molecular geometry. Remember, when the non-bonding is 0, electronic and the molecular geometries are always the same. So that means this is going to be tetrahedral. Okay. So if we looked at a microscope at that molecule there, it would look like a tetrahedral. Remember, you can't see the non-bonding electrons. You only see what's bonded to it. But what determines the molecular geometry is the electronic geometry. That's why you need to determine it first. Okay, so let's look at another molecule. Let's look at that. Okay, so what's the central molecule there? Nitrogen, only one, nitrogen. So we're going to do the analysis on the nitrogen. Okay, how many electron groups? How many electron groups? Remember, I'm not talking about bonding or non-bonding. How many groups of electrons are there? Sometimes electron groups are called electron domains. Same thing though. So how many electron groups are there? Yeah, 4. That automatically means electronic geometry is tetrahedral. Okay. How many lone pairs are on that? 1. How many how many bonding? 3. Those have to be equal, no exceptions. Okay, no exceptions. So basically we're accounting for all what the electrons are doing, whether they're bonding or not bonding. But the total is always the number of electron groups. So this is going to be 1 and 3. So a 1 and 3 is trigonal pyramidal. Okay, there's trigonal planar, flat, 2-dimensional. Trigonal pyramidal. Looks like a little pyramid, 3-dimensional, okay? So don't just say trigonal. It's got to be one or the other. Everyone okay with that? Let's take water. Okay. How many electron groups? Four. You have to count all the electron groups, including the non-bonding ones. So 4 automatically is tetrahedral. Okay. How many non-bonding? 2. How many bonding? Okay. If it's 2 and 2, that's called bent. So you can see when we get to 5, there's going to be more combos. We get to 6, there's even more combos. Now, the first thing you need to do is when I give you a formula, like that, the first thing you need to do is to do a Lewis dot structure. Step number 1. Step number 2 is find the central atoms. So if we were to do a dot structure to that, wait a minute, let's that's kind of complicated. Let's do it differently. Okay, so the dot structure for that is what we did yesterday. Okay, how many central atoms are there? Huh? 2. Remember, central atoms defined as having to have 2 bonding atoms. Okay, how many does this bond with? 1. Just carbon. So that is not a central atom. What about this oxygen? How many is it bonded to? 2. So it's a central atom. What about the carbon? It's got 3. So there's 2 central atoms. Okay. That means we have to do this analysis for each one. So let's do carbon first. How many electron groups are around carbon? And remember, cover up the atoms. They have no play here. So how many groups is that? 3. Remember, the double bond and triple bonds count as one group. So it's 3. Three is, remember, trigonal planar. Okay, as far as the molecular geometry goes, how many are bonding? How many are bonding? All of them are 3. Non-bonding, remember, these 2 have to add up to the 3. So that automatically means there's no bonding. Okay, so whenever it's 0 on non-bonding, electronic and molecular geometries are the same. So it means that central atom now, not the whole molecule, just that central atom. Is also trigonoplanar. Okay, so we have two central atoms now. Okay, let's do the oxygen. Okay, so when we do the oxygen, we have to cover everything else up. So this oxygen, not that one, this one here. So we're going to cover everything up. It's like that. So how many electron groups does that oxygen have? 4. Okay, we have 2 electron pairs and 2 bonds. That's 4 electron groups. Four electron groups is tetrahedral. Okay, how many bonding? 2. How many non-bonding? Okay, and we have 2 and 2, it's bent. So that central atom, the oxygen central atom, it's sort of like water. So I didn't really draw that correctly, did I? I should have drawn it bent. So let's correct that. That would be a more accurate appearance of that. So just right off the bat, look at this molecule. I think that's polar. And what I said about oxygen, is oxygen 2 single bonded present? Yes, so it's polar. Don't even need to not go any further. It's also very unsymmetrical. Unsymmetrical molecules tend to be very polar. All right, well, that's what we're going to be doing on the worksheet today. So step 1, Lewis dot structure. Step 2, identify central atoms. And then make a space for the analysis of each central atom. Okay, also be putting in angles, proximate angles for now. Okay. So this angle here, because it's trigonal planar, it's going to be 120. And this one here, and that is determined by the electronic geometry. On the second central atom, the oxygen, that's going to be based on 109. It's not going to be 109 because it's not a perfect tetrahedral. And then determine whether it's polar or not. Okay, so that's the essence of this worksheet. There's a lot of practice. And if you've never done this before, you really need to practice. So